Hello everyone, welcome to another session of the GSE group. It's a pleasure to have you all here. This current session is from Fabio at EPV Technologies. You should be able to see my screen. This is a pre-recorded session and which Fabio from EPV has pre-recorded. It is about measuring the integrated accelerator for zEDC. We'll be starting in a minute. We're just letting some more people in. So this is a pre-recorded session, but Fabio and Danilo, both from EPV, will be taking questions at the end. So we'll just give it another minute just to allow a few final people to come and join us. Ask if your microphone isn't muted, please mute it and turn your cameras off. Right, looks like everyone is here and attending. So we will start playing the session. As mentioned, this is pre-recorded, but we will take questions at the end from Fabio and Danilo. We'll be asking for you to give session feedback at the end of the session, and there is a slide giving some details of how to enter the GSE charity raffle. So if you would like to enter, please take notes on that as it pops up. You can submit questions during the presentation, but if you could, but we will answer them at the end. So thank you everyone. I will get the presentation started. Speak to you at the end. Thank you.
Hello to everybody. My name is Fabio Massimo Ottaviani and I am the Technical Director of EPV Technologies. Today, in this presentation, I will talk about the integrated accelerator for the zEDC. This presentation is derived from a white paper we published in our newsletter. So if you want to have more details, you can go to the website that is indicated in this slide and ask for it. Before starting with the presentation, I am glad to invite you to consider the possibility to... Let's start with the introduction. In the last years, we have seen an explosion of data, which has been driven by new technologies and applications. This has happened also in the ZOS systems, and for this reason, you have to be very careful when you do your capacity planning for disk storage. I remember one of our customers that had a rule of thumb, which says that they have to double their storage subsystem size every 3 years. Probably they have also to review this rule of thumb by looking at the new trends. Of course, the evolution of storage subsystems have become more and more efficient in solving this kind of issues. So we have more powerful storage subsystem, but they can only solve part of the problem. Because when the data are inside the host, are inside the system, applications have still to manage this huge amount of data with consequent resource utilization and performance issues. Another important point is cryptography. If you are following the IBM strategy of pervasive encryption, you have to encrypt more and more data. And so this is another important issue that had to be considered. A more complete solution to try to address all these problems is compression. Compression may greatly reduce data size, and this will provide great benefits in terms of both storage usage and performance also inside the system. And it can also provide a lot of benefits if you decide to encrypt the data, because the less data that you have to encrypt, the better it is. As you know, software compression has been available for many years. The main issue with software compression is the number of CPU cycles which are needed to execute compression and the compression instructions. So you know that when using this kind of compression, the cost to pay can be very high. With the zEC12 machines, IBM introduced Z Enterprise Data Compression, zEDC, which is a hardware and software solution which is based on a specialized adapter for data compression, the zEDC Express card. And so with this solution, IBM addressed the issue of software compression, trying to move the burden of these kind of operations to the hardware. With the Z15 machines, IBM made a jump forward. They eliminated the need of the zEDC Express card by introducing the integrated accelerator for zEDC. We will call it simply accelerator in the following of this presentation. Let's now have a look to the most relevant characteristics of the hardware and software implementation of the accelerator. The hardware component of the accelerator is a new coprocessor which is included in the Z15 chip. This coprocessor is shared by all the processor cores which are in the chip and are using the same level 3 cache. You can see in the picture that is identified as NXU and is delimited by a red box for you to see it easily. This coprocessor, of course, is included in the chip, and therefore it will provide a much higher compression bandwidth than allowed before by the zEDC Express cards. A very important new feature of the accelerator is that it can run synchronously with respect to the invocation program. So you can run a synchronous compression request to the accelerator by any problem state application which exploits the DFLT-CC on-chip machine instruction. At the same time, the accelerator will continue to support the same asynchronous model as used by the zEDC Express card, with a major difference. The major difference is that the zEDC Express card, the PCI cards, are not used anymore, so the compression request is managed directly by the system assist processor, and it uses extended asynchronous data mover subchannels. These subchannels are a special kind of subchannels which are automatically defined IPL without no need for the customer to make any definition. A very positive aspects for customers already using the zEDC Express cards for compression is that no hardware or software configuration changes are required to exploit the accelerator. So when these customers will migrate from their current machines to the Z15, there is no change they have to make. So everything will still continue to work. It's important to note that IBM already announced that the zEDC Express cards will not be available in future machines too. So they have been completely replaced by the accelerator. As mentioned, it is now possible to run synchronous compression and decompression requests to the accelerator. Of course, this will provide much better performance. The synchronous exploiters at the moment are a certain number of languages and products which are reported in this slide. You can note that Java is written in green because one of the case studies that we will discuss later in this presentation will refer to a Java exploitation. For what concerns asynchronous compression and decompression requests, the exploiters are the usual ones. In this list, you can see we have access methods, products, and ZOS functions. Also in this case, we highlighted in green one of them, CUSAM, because one of the customer case that we will see later will refer to this kind of exploitation. Let's now talk briefly about cost. This is a very interesting topic, especially for managers. Before Z15, zEDC required both chargeable hardware, the zEDC Express card, and the chargeable ZOS feature. The good news is that with the Z15 machine, the zEDC function, as we saw, is now built into each chip, so it's included at no additional hardware charge. The bad news is that from a software cost perspective, the asynchronous exploiters still require the chargeable ZOS feature, also on the Z15 machines. Let's now look at the SMF measurements which are available to measure synchronous compression and decompression request when using the accelerator. The zEDC synchronous requests are managed inside the Z15 chip by exploiting the accelerator. For this reason, IBM provides this information by using the CPU measurement facility, which, as you know, provide a certain number of counters which are collected in SMF 113. There are 4 new extended counters that are available to measure this kind of compression and decompression request. You can see here we have the counter E247, which are the cycles that are spent to access the deflate unit. This is an important point because these are synchronous requests, so the CPU is spinning while waiting for the accelerator to process the compression and decompression request. So it's very important to know how many cycles we are using both to access the deflate unit and also when using the deflate unit, which is the next counter, E252. Other 2 important counters are the E264 and 65, which provide information about the compression and decompression request executed. By using the first formula in this slide, you can calculate the total number of CPU or ZIP cycles that are used when accessing the accelerator or spinning while waiting for the accelerator to execute the synchronous instructions. We mentioned both CPU and ZIP because you know that the information provided in SMF 113 refers to a specific logical processor. So the request can come from a workload that is running on the CPU or from a workload that is running on the ZIP. And you are able to distinguish these 2 kinds of usage. A more important formula is the next one, which tells us how much in percentage of the total CPU or ZIP used by the helper is due to synchronous requests which are served by the accelerator. So as you can imagine, we expect that this number will be not too big. Another interesting formula is the one which provides the CPI, which is the number of cycles per instruction for this kind of compression and decompression synchronous request. This is very interesting because it can give us an idea of what is the effort of a compression decompression request. And we will see that the numbers are really surprising in some way. Let's now start looking at some customer case. So this is customer case 1. You can see in this graph the number of deflate synchronous instructions invoked by application running on the standard CPUs. You can note that there are a very low number of requests. So in 10 minutes interval, which is the RMF interval used at this customer site, we have some thousands of requests, so a very low number of synchronous compression and decompression request. More interesting is this graph, which represents the number of deflate instructions that are invoked by application running on zip. You can see that the activity is normally very low, but there are spikes that reach 1 million and over at almost regular pace. We will see the reason for that in the next slides. The first thing we noted in this analysis is that all the peaks fall around the hour expiration, not always exactly at the hour expiration, but very close to that. So we try to understand what was the workload creating these peaks, but unfortunately there is no information in SMF records at the address space level, so we don't know which are the address spaces issuing this synchronous instruction for compression decompression. After a short investigation, we verified that at this site they implemented one of our products, APV4ZOS, in refresh mode. This is a tool which allows you to analyze system performance in the previous day, but also on the current day with a delay of 1 hour, generally speaking. So it's a kind of near real-time product. To allow this product to work properly, every hour this customer was dumping the SMF data, compressing them by using another tool that we provide, which is a PVZip, and then send the compressed data to the PV server, because as you probably know, we process SMF data outside of the mainframe. So all this process is done, generally speaking, at the hour. So it's very likely that this application will be the one creating all these peaks, because the application, the APVZip application, which compresses the data, is an application written in Java. And it, of course, runs on the zip. And it uses the zlib compression library, which is one of the possible library you can use to exploit the accelerator. So putting all these things together, we are pretty sure that the spikes that we saw in the previous graphs are due to the activity of a PVZip. Another interesting thing to note is that this customer was not using zEDC SPS cards in the past. And they had to change nothing in both PVZip and the PVZip code and the system parameters, but immediately after the upgrade to Z15, it's PVZip, and this can be true for any kind of product exploiting the zlib library in Java, automatically started exploiting the accelerator. From the point of view of CPU and zip consumption, we can say that in this case the consumption of the CPU due to synchronous requests served by the accelerator was negligible, but as we saw, also the number of requests was very low. For what concerns the zip, the highest peak for zip was 0.25% of the total zip usage, so it was really not very high. On the other hand, the CPI, the number of CPU cycles per instruction, was very high in both cases. By using the formula that you saw before, we estimated the CPI for the request coming from the CPU. And you can see here that the cycles to access the next accelerator unit are not very high. On the other hand, the cycles using the coprocessor are much higher, and you can see they are normally at 10,000 level, so 10,000 cycles per instruction, with some peaks also up to 14,000. The situation for the request coming from zip is very similar, even if not identical, but you remember the zip workload is much higher than the CPU workload. But you can see here, however, that the cycle to access the coprocessor, the next accelerator unit, are again very low, and the cycle using the next accelerator unit are much higher. So you can see the level here is at around 9,000. This is the normal level, with the spikes which reach 14,000 and more normally are around 13,000 or something in the middle. The message here is that there are a lot of cycles which are needed to process a compression and decompression request. Normally, when you access the data in the level 1 cache, the cycles that you need are very few, just 1 or 2. In the level 3 cache, which is the one that belong to the chip, so the same place where the next accelerator unit is, normally are around less than 100 normally, but it depends on where you are going to. So if it's a chip in the same place where you have the processor is another chip and so on. But generally speaking, you expect to have 100 maximum cycles for an instruction when you are going to the chip where your processor is. And in this case, you can see that the number of cycles needed is 10,000 and more. So it's really a very heavy instruction. So the compression instructions are very heavy from this point of view. Okay, let's now look at the measurements that we have available to measure the asynchronous compression and decompression requests to the accelerator. As mentioned, before Z15, the zEDC Express cards were based on a PCI card. For this reason, the measurements available were provided by the SMF74 subtype 9. Now, the situation is different because the PCI cards are not used anymore, and so we had to use a different subtype of SMF74, which is the subtype 10, which provides the EADM statistics. These are one of the most important metrics that we normally control are the compression and decompression ratios. They can be easily calculated with the following formula, which use some of the fields that we saw in the previous slide. Very good news is that, as in the past, information about compression and decompression activity is provided also at the address space level. So, if you are using the old zEDC Express cards or if you are using the accelerator, you still have this information in SMF30, and this is very important. Another important thing is that the accounting is very good. So if you sum all the address space activity and you compare the values with the data coming at the system level from SMF74 subtype 10, you see that the values are almost identical. It's important to note that when moving to the accelerator, some of the fields which are provided in SMF and described in the manual are not valid anymore with the accelerator. So we will not report here these fields, but you will find them in the SMF manual. However, in the manual is also specified that these fields are not valid anymore for the accelerator. These are the fields which are relevant for compression, decompression, which are provided in SMF30. So for each address space in the system, they are almost the same that we found in SMF74 subtype 10. The major difference is that we don't have the detail of compression and decompression requests, but we have just one field included both this kind of request. Let's now look at some measurements coming from the customer case 2. The graph in this picture shows the number of asynchronous compression and decompression operations. These are data at the system level, so they are provided by SMF74 subtype 10. You can see we have a green bar, which are the compression operations, and we have a blue bar, which are the decompression operations. You can note that the number of the compression operations is normally very low, and only around noon there is a peak. By using a formula provided in the previous slides, we calculated the compression ratio. So the compression ratio, you can see, it's very stable. It's generally between 3 and 3.5 with some small variations. By analyzing the SMF30 records, we were able to understand where these compression requests were coming. And the answer was that most of the compression requests has been issued by the DB2 master address space of 3 DB2 subsystems running in this system. And this activity is due to the writing of compressed archive logs, which, by the way, are using the CUSAM access method. You can see that we indicated with the light green the megabyte after compression, with the dark green the megabyte before compression, and with the red line the compression ratio. You can also note that the compression ratio is generally included between 3 and 3.5, as we saw at the system level. So this confirms that most of the activity is performed by these address spaces. As mentioned before, the accounting to the address space looks very good. In this graph, we reported the compression operation and the compression operation taken from SMF74. They are reported in dark blue and light blue. And with the red line, we included in the graph also the SMF30 compression and decompression operations, which, as you know, are provided by just one metric. And you can see that the numbers are pretty identical. And this is true not only for the compression and the compression operation, but also for the bytes compressed or decompressed, which are provided in both records. Now, some final considerations. The first important consideration is that no special action is needed for customers which already are using the zEDC Express card to run their asynchronous request to the accelerator. So there is really no change that you have to make. Applications may also run synchronous compression decompression requests to the accelerator, and this is a completely new possibility introduced with the Z15. An important consideration is that the accelerator will provide a boost in throughput and performance for both request types, because if the request is asynchronous, it has not to go anymore to the PCI cards. And if the request is synchronous, all the activity is inside the same chip. So in both cases, you will have much better throughput and performance. For what concerns the activity of performance analysts, there is a new set of measurements that needs to be understood and used to be able to analyze the compression and decompression activities with the Z15. You need to analyze SMF 113 because they are needed to measure synchronous requests, and as we saw, they can be used also to understand how much of the CPU and the zip usage in your system is derived by the compression decompression activity. Also, for what concerns the asynchronous requests, there is a new subtype of SMF74, so you should not use anymore the subtype 9, but you have to use the new subtype 10 records. For what concerns the SMF30 and the address space activity, I assume that you already were using this kind of records to analyze compression and decompression. This is the end of the presentation. thank you for your attention. Now it's time for questions.
Okay, so I'm going to unmute Danilo and Fabio's microphones. Does anyone have any questions for either of them? Danilo, are you there?
Yes, I am.
Excellent.
Yeah,
So,
I guess Fabio as well. So if
Yes, I'm here.
yes, we can hear you, Fabio and Danilo. Excellent. So we don't currently have any questions through from anyone, but I'll give everyone a moment to send questions in. Whilst I'm doing that, I would just point out here is the information for people regarding how to leave some session feedback. So you can follow this link. This session is 6 a.m. and the feedback is always appreciated because it helps us to figure out what people want from these sessions and figure out what we do next year. And fingers crossed, hopefully we can return next year to face-to-face sessions. So we've had a message from Brett saying, can you put submit session feedback into the chat? So I will put the link into the chat to everybody. Give me a moment to get out of here.
Okay, anyway, you have our details, and so if anyone will have a question even later, they can send us directly their questions or their comments, and we will answer to them by email.
Yes, I've got Fabio's email address on screen and the email address of EPV, where you would be able to reach both Fabio and Danilo. We'll give everyone another moment or two just to submit questions. Give everyone to just another moment. So John said you can click the bottom of the session on my agenda on the conf website. I've posted the link for the feedback in the chat window, which I hope everyone can see. If there is any trouble filling that out, then please get in touch with us at the GSE community. We'd be happy to help. So I don't think we're going to get any questions through, Danilo. So I think we will leave.
Okay.
We'll leave the session there.
I hope to meet you all again next year live, which is much better than these virtual sessions that are good, but they are not the same.
We hope to have you back in the UK, Danilo, next year, doing these sessions face to face with us all. We think it will be a much better scenario for us all.
Let's hope so. Okay.
Okay, right. Well, we've had no more questions through, so thank you for your time, everybody. The next session in this stream will be at midday, and I hope to see you all on that session. Thank you, everyone. Goodbye.